Okay, so let's go over the sheet. So it gives you a real life example about camping, and it asks you which of the processes is exergonic there. So there's two processes there, one with the arrow going down and one with the arrow going up. The exergonic one is what, Joel?
The exergonic one is the firewood and O2, which goes into the CO2 and H2O.
That's correct. All right, so the burning of firewood, that's a very exergonic process where energy is released. And so that leaves B, which of the processes above is energonic and has work done to it, is the heating of the cold water. So the cold water to hot water. And so notice in the stem of the question it says, if you have ever been camping, you may have used coupled processes to make yourself some hot cocoa in the evening. What they call that when you have an exergonic reaction and driving an endergonic reaction. That exergonic reaction that releases energy provides the energy for the endergonic reaction. We say that those reactions are coupled together because the endergonic reaction could not happen. You could not heat the cold water and make it hot without the exergonic reaction. So they call that coupling or coupled reactions. So they occur together. And so number 20 there, consider the coupled processes below. And so this is more of a real life reaction that would occur in cells. Which of the processes is exergonic for this? What do you think, Jacob? Yep.
For the
Yep. Which process is exergonic?
glucose and oxygen to CO2 and H2O.
Yeah, absolutely. So that process releases energy. You're breaking down glucose into carbon dioxide and water. This is the opposite reaction of photosynthesis. Do you guys remember what that's called? I remember when you break down glucose. Olivia? Cellular respiration, absolutely. And so that energy that's released then drives an endergonic reaction. In this case, for B, that would be the formation of ATP, putting the phosphate onto ADP and making ATP. So that reaction needs energy, and so that's why it's important when we say we need glucose for energy. That's what it does. When we break down glucose, some of that energy released goes to make ATP. All right, and so that was just a little review from where we left off yesterday, talking about ender and exergonic reactions. So let's take a look at the notes again. So pull those out. I think we left off, if I remember correctly, at the graph. Yeah. I lost it. Oh, there we go. Yeah, there we go. Throwing stuff around here. So I think this is correct. We finished the last line. All right, so let's look at this. So this is another way to look at exer and endergonic reactions. And so let's look at what the graph is showing here. This is the progress of the reaction, so this is time from beginning to end. And this is the free energy of the reactants and the products represented by a bar graph. So free energy, remember, is the energy available to do work. And so then we can think of this as G initial, and this is G final. So we talked about that yesterday, final minus initial to get your change. And so we can see that the reactants have a lot of free energy. The products have little free energy. So if you remember the law of thermodynamics, that energy can be neither created nor destroyed. That energy that was once in the reactants has to go somewhere, and so that energy is released. It's not destroyed, it doesn't disappear. That energy is released into the environment, and some of that energy can be used to do cellular work. So when we see here these dots here, the difference here is the amount of energy released that's then available to do work. And so when we talked yesterday about the change, you guys okay over there?
We're on the wrong page.
Oh, okay. I was wondering what was going on. You look so confused. All right, you found it?
Yeah.
Okay, all right. Final minus initial. And so that's what we're doing here. Final minus initial, so that the final products have less free energy. And so, so we talked about that yesterday. So low minus a high number, and we get a negative number, and your delta G is less than 0. All right, and so that is an exergonic reaction. Which is this similar to, a catabolic or an anabolic pathway? Talked about that yesterday too. A catabolic pathway. Catabolic pathway, breaking down substances. All right, breaking down substances and releasing energy. And so another way, when we see exergonic reaction, a catabolic pathway is really describing the same thing. Catabolic pathways involve exergonic reactions. Does that make sense? Energy is released in both of those, so it's two. And these are considered spontaneous. So reactions that release energy like this are considered spontaneous reactions. I want to point out that sometimes people think spontaneous means that they automatically happen. And that's not necessarily the case. Let me give an example of gasoline. Burning gasoline is a very exergonic reaction. The gasoline molecules have a lot of free energy. When we burn gasoline, a lot of energy is released into the environment in the form of heat and light and so on. But if I had a gallon of gasoline up here, would it spontaneously by itself combust? No. What would I have to do to it? I'd have to light it. I'd have to have some kind of spark. And it only takes a little bit, just one little spark on there, and we get a very exergonic reaction. We get a big explosion, lots of energy released. But that is still an exergonic reaction. The definition of an exergonic reaction is that the reactants have more free energy than the products, and you get energy released. We'll talk a little bit later that most exergonic reactions do require a little bit of input of energy. We'll talk later about that. The energy input is called an activation energy. You have to put a little bit in to get a lot out. So exergonic reactions don't necessarily mean that they spontaneously happen, even though they're called spontaneous reactions. Spontaneous means that more free energy, less free energy, a release of energy into the environment. Some of that energy can be used to do work for us. And so most exergonic reactions require that input, because if you think about this, if everything that if all the gasoline just reacted without that input of energy, we'd have no gasoline on the earth, because it would spontaneously, it would just be reacting all the time. All right, so it stabilizes it, all right, and so you have to have this little bit of input of energy. All right, so this is your exergonic reaction. So then your next graph shows you your endergonic reaction. So endergonic reaction, the opposite here is happening. So you have your reactants having less free energy than your final reactants. And so that energy cannot be created, right? It doesn't come from just out of the nowhere. That energy comes from the environment, so it absorbs energy. So this could be absorbing heat from the environment. Light can be something that causes a reaction to happen. Any energy source from the environment. And so it's absorbing that energy, and that energy now is going to be stored in those products. And so the products have more free energy than your original reactants. And so again, to figure this out, it was delta G is final minus initial, and so we see that our final is greater than our initial, and we get a positive number every time. All right, and so the endergonic reactions, this would be part of what kind of pathway? Anabolic. All right, so another way to say endergonic pathway is this anabolic pathway. You need energy. All right, so let's apply this to this. I didn't put this into your notes, but this is just a little something I want you to look at to try and figure out based upon what we've talked about. So what we have here is 3 reactions, 1, 2, 3 each row. So if we look at here, hydrolysis of sucrose and water, our products are glucose and fructose, and then it gives you the delta G, all right, the change in free energy. Notice it says below, the table shows some reactions, those 3 reactions, and the absolute values of their associated free energy. So I did not put in front of this a positive or a negative in front of the delta G. What I'd like you to do, and you can talk amongst yourselves in doing this, for each reaction, I'm going to think about what you would expect the delta G to be. Would you expect to have a positive or a negative in front of there? And then figure out which reactions you would consider spontaneous. All right? So look at those 3 right now. You can, like I said, you can talk amongst yourselves to see if you can figure out what those things would be. All right, let's come together and talk about this. So, the first reaction where sucrose and water form glucose and fructose. So really what we're doing, sucrose is a disaccharide, right? So we're taking a disaccharide and breaking it down into 2 monosaccharides. So delta G is 7. Madeline?
I felt that it was exergonic.
Okay, which means what in terms of the positive and negative?
It's negative.
Okay. Yeah, it is negative. All right, so exergonic reaction, larger molecules broken down into smaller molecules, and energy is released. You guys get that right? All right. All right, so that's negative. Triglyceride detachment. We talked about triglycerides being a lipid, and it has glycerol, so it's when it says glycerol, and notice it says fatty acid, 1 fatty acid, so here's your glycerol molecule, and remember, to make a triglyceride, usually there's 3 fatty acids, hence the tri in there, so we're starting to make a triglyceride by adding 1 fatty acid, that first fatty acid, and making a monoglyceride, which means that it has 1 fatty acid there. So it has 3.5 here. Would this be a positive or a negative? Megan?
We said positive and anabolic because you're creating something.
That's right. All right, absolutely. You're building something larger, so this would be a positive. All right. You guys good? Doing okay so far? All right, awesome. And then photosynthesis. We talked about photosynthesis yesterday. Carbon dioxide and water. It formed glucose and oxygen, and we have a big number here, 686 compared to these other ones. Really big number. Positive or negative there? Erica, what do you think?
Positive.
Yeah, this is a positive. Absolutely. Energy is required to make your glucose molecule. What's the energy form that's required that we talked about yesterday? Sunlight, right? Sunlight is absorbed in there, and then that's how the glucose and oxygen, the glucose has more free energy than the carbon dioxide in the water, and so energy is needed there. So, so that would be an endergonic reaction. So, when I ask you which reactions will be spontaneous, what is our answer there? What do you think, Ben?
For the first one was spontaneous, the second two.
That's right. The first one is spontaneous, and the second 2 were not. All right. So remember that when your delta G is negative, that is an exergonic reaction, which means that energy is what? Released. And this is another way to say spontaneous. And so the only one that's true about is that first one. All right. These 2, the delta G is positive, which means it's endergonic, which means that energy is needed. And we could say it's non-spontaneous, all right, in that. So that's kind of the thought process there, okay? So now let's go a little bit more in depth with this. Let's go back to this exergonic picture. What I want to do is relate one of the equations that we talked about yesterday. So when we talked about, like when I wrote here that delta G is final minus initial, one of the other equations, how do we figure this out? How do we figure out what G is and what G is here to get a difference here? So we wrote in our notes this equation here. Ring a bell? Okay, so we wrote that in our notes. So if you have room on the side, you can do this for this. So I'm going to talk about this, how it relates to what we just looked at here. This right here is one of the equations on the AP Bio equation sheet. So far in this class, we've done almost this whole back side of this equation sheet. So we've done the water potential, we've done surface area to volume ratio, we've done C1, V1, we've done pH, and down here is this equation right here. This equation is called the Gibbs free energy equation from the scientist who came up with it. So let's just quickly review, because we wrote it down yesterday in our notes. So this is the, G is what? The energy available to do what? Energy to do work, right? This is called enthalpy. Does anybody remember what that meant?
That's the total heat energy.
Yeah, total energy. It could just total energy, period. It doesn't have to be heat. Total energy in the system minus, and then this T delta S. Delta S is entropy. Entropy, do you guys remember what entropy is? It has to do with the second law of thermodynamics. Second law of thermodynamics says that we increase entropy in the universe. Olivia? Yeah, the disorder. So remember that disorder, what we talked about is why it's multiplied by the temperatures, because when you increase the temperature, the disorder increases. Molecules start moving faster, and so it's more disorderly. Decrease the temperature, exactly opposite occurs. This energy is unusable energy. So the energy available to do work is taking your energy that you have minus anything that's not usable, and that's the disorder. Okay, so that's the T delta S represents the disorder. All right, and so unusable energy. And so that's a quick little review here. So what does this mean when we say delta S? Well, delta H here. So delta H is the final minus the initial. So let's just look at this with this reaction here. So total energy, this is initial and final. What do you suppose has more energy at the beginning or the end? The system, the beginning, right? And so when we look at this, so H initial, the total energy at the beginning has a higher energy, final, lower energy. Let's just look at mathematically here. Lower number minus higher number. What kind of number are we going to get here? A negative, right? So in this equation here, for an exergonic reaction, delta H is going to be a negative number, always. All right? So then we look here at this part of the equation. Let's look at delta S. S final minus S initial. Now S, remember, is disorder. So do you think that there's more disorder or entropy here initially or here at the final state? So initial versus final. Which one has a greater entropy? Scott? It would not be the initial. So it's the final. Can somebody tell me why it might be the final? It's the explanation there.
Because when the energy escapes, it's like not like concentrated, so it's
That's right, that's right. This energy here is in the chemical energy in this nice neat molecules here, the reactants. When they react and energy is released, like some of the energy can be heat and so on, and so that creates more disorder. And so therefore, at the final state, the universe has more disorder than at the original state, okay? And so when we look at that then, we're gonna have higher entropy in the final state, right? And lower in the initial state. So if we look at this mathematically, larger number minus a smaller number, we're gonna get what kind of number? Positive, right? Those people watching the video. So we're gonna get a positive number here. So then when we look up here, then this number, if this is a positive number, we're gonna have a negative minus a positive number. We're gonna get a what kind of number every time? Negative minus a positive number. Negative, right? So that's why we get a negative number. So this is why it is below. What I'd like you to do is take this, what we just talked about, with an exergonic reaction, and I'd like you to do the same thing with an endergonic reaction. So we look at the next slide. What I want you to do is look at this equation, kind of do just what I did here, do final minus initial, what kind of number are you going to get, and ultimately, what kind of number are you going to get here. So I'm going to do just what we just did. What for endergonic?
Can I go back?
Do you have your plan? You like Mr. Cole?
Yeah,
Yes.
planners.
Okay, so let's look at this. So for an endergonic reaction, so let's look at delta H and figure out final minus initial. So let's see, what can I call Tim, what do you think? Which one has a higher total energy, beginning or end? The end. So we have a higher number here, lower number here, higher minus lower will give you a positive number every time. So therefore, we have delta H as positive. Then we look at entropy, final versus initial. More disorder here in the universe or more disorder here? What do you think? Grayson, what do you think?
I think that there's
Less
less in
in the final, absolutely. There's more disorder here. Can somebody explain why that is? Why there's more disorder here versus here?
Is there more free energy?
This has more free energy.
No, the reactants have more free energy, right?
Actually, no, the reactants have less free energy. The products have more free energy. Where did that additional free energy come from? Yeah, the energy outside of the universe. So they've taken energy, it could be heat energy and so on, which is the most disorderly type of energy, that can be absorbed by the reactants to create the products. And so therefore, they're taking energy that's less orderly and making it more orderly by putting it into the molecule and into the bonds of the molecule. And so therefore, the initial, I should say, has a higher disorder than final. All right, so when we do this, lower number minus a higher number, we get a negative number. And so delta S up here is negative. So then, if we look here, positive number minus a negative number. What kind of number we get? A positive, right? So hence, endergonic reaction, positive every time. All right? And so when we look at, and I gave you guys this sheet, the formula sheet. When you look at this, and this is what you'll be given on the test, both on my test and the AP test. Down here, it gives you the equation. And it tells you, I'm going to tell you what it tells you with this. It tells you that delta G is free energy. It doesn't say energy available to do work. So they're assuming that you know what free energy means. They tell you that delta H, here it says delta H equals change in enthalpy. It doesn't say total energy. They're assuming that you're going to know that enthalpy means total energy, all right? And then it says delta S is the change in entropy. It doesn't say disorder, so you need to know that entropy means disorder. And then it says T is the absolute temperature in Kelvin, and that's all it tells you, so you have to know what? That Kelvin is the degrees Celsius plus 273. Okay, and so that's what you'll be given, and so you'll be expected to know what all those terms mean and so on. Okay? All right. So, so let's move on here in the notes. So let's go through some examples of exer and endergonic reactions that happen in cells. So we need exergonic reactions to do work. So what are the types of work that cells do? There's mechanical, transport, and chemical. And we'll look at each one of those in just a few minutes here. Mechanical is kind of moving stuff around. Transport is like moving things in around the membrane into or out of the cell. Chemical is chemical reactions. So we manage in our cells energy resources to do work by this energy coupling. So remember that I alluded to the fact with that first problem in the class where we did the firewood and the heating of cocoa using an exergonic process to drive an endergonic one. So the exergonic reaction releases the energy to drive the endergonic reaction. Not too fast? Are we good? Saw some people still write. So, in comes ATP. So I've talked about this molecule before. Adenosine triphosphate is the cell's main energy source in energy coupling. ATP is an adenine plus a ribose and 3 phosphates. Adenine plus a ribose, this right here together, make the adenosine molecule. So that's why it's adenosine triphosphate. And the tri is from the 3. We should know what these molecules are. How do we know adenine? Derek? It's not actually not part of amino acid. It's part of another molecule that we've talked about. Another macromolecule, Jana? It's found in DNA. In DNA, it's one of the nitrogenous bases, the A, T, C, and G. Adenine is A. So this is I'm just going to, nitrogenous base in DNA. Well, guess what? It's also an ATP. How do we know ribose? What is ribose? Vision, if you can tell me what ribose is.
Sugar.
This is a sugar, and where do we know this sugar from? What molecule do we say that this sugar was a part of?
RNA.
Tristan?
RNA.
RNA, absolutely. So this was a pentose sugar in RNA. Pentose means what? 5 carbons. So that's how we know those. So these two are both used in RNA and DNA, but also in ATP. All right, so here's your structure. Here's the adenine, here's the ribose, and here are your 3 phosphate groups. I want to point out here that these phosphate groups have a negative charge. What do we know about like charges? Do like charges attract or repel? Repel, right? If you ever try to put 2 negative ends of a magnet, you have to be like super strong to put them together. All right, they repel. And so what happens is that these phosphate groups here, we have some unstable bonds here between the phosphate groups. And that's important to make it a very high energy molecule. All right, so when the bonds between the phosphate groups are broken by hydrolysis, remember adding water, energy is released. And the release of this energy comes from the chemical change to a state of lower free energy. So what does that mean? When we break down ATP, if we do that same graph where we have the delta G and free energy and time, that ATP is your reactant and your products are ADP and a phosphate. Your ATP has higher free energy than your ADP, and what happens then is energy is released, and that's why it's an exergonic reaction and why it can drive endergonic reactions. So that's what this picture here is showing you, is the breakdown of ATP into ADP and a phosphate. So they take off the phosphate here. So here are your 3 phosphates. Here's your addition of water. That's your hydrolysis, right? Breaking it down. And then we get ADP with the 2 phosphates. And notice here it says P with a little sub I, and they call that inorganic phosphate. What that means is this is a phosphate group not attached to a molecule. Notice it's sort of floating around by itself here. It's not attached to anything. So phosphate group not attached to a molecule. And notice here, energy is released. Some of that energy is released as heat. Can we use that? No. And then some energy is available to do work. And so this. So therefore, a very exergonic reaction. So this is going to provide energy to do cellular work. Some of the energy that's released is going to perform. So how does ATP perform work? So the exergonic release of the inorganic phosphate is used to do the endergonic work of the cell, stuff that needs energy. When ATP is hydrolyzed, remember that's when hydrolysis has happened, so it's been broken down, it becomes ADP, adenosine diphosphate. And so then the phosphate is not attached to it. So let's talk about this picture here. So this just talked about which side of the equation, or which side of this circle, the left or the right. When ATP is hydrolyzed, left or the right side? The right side here. ATP is broken down into ADP and a phosphate. Energy is released for cellular work. So that's what this just was described. I want to talk a minute about the second half of this circle here. This is the regeneration of ATP. ATP is used to do all of our cellular work, and can you see that if we keep breaking down ATP into ADP and a phosphate, that eventually we'll run out of ATP. So therefore we have to have a way to regenerate and replenish our cells with more ATP so we can use it again. So ATP is always recycled in the cell. So the thing is though, to make more ATP, you have to put the phosphate back onto ADP to regenerate and make more ATP so you can continue to do cellular work. This process requires energy. It takes energy to put that phosphate back on to make ATP, and so therefore we have an input of energy. So this right here is an endergonic reaction where that energy is needed. So it says here energy from catabolism, exergonic energy releasing processes. So let me explain here what the big reaction that provides the energy to make ATP is, and we talked about it earlier today, is cellular respiration. Cellular respiration, we'll put in parentheses here, is breaking down glucose and releasing energy. This is an exergonic. The opposite of photosynthesis. This energy released is the energy that's needed to put the phosphate back onto ADP. So when we learned about glucose and said glucose is an energy molecule, our cells use glucose for energy, that's what we do. We break down glucose, that energy released from the glucose regenerates our ATP, and then we can continue to break down the ATP to make to do cellular work, and then we continue to break more glucose down, and so on. And so your cells are constantly, right now you are using thousands and thousands of ATP, even if you don't even move, all right? And so, so your cells are, while they're breaking down ATP, are doing this process as well to regenerate it so that you always have ATP to do cellular work, all right? And this is where we'll stop. Let me explain real quick here. Let me explain real quick on this, the two other things. The one that says free energy at the top here, free energy, there's some practice with that equation. This is homework tonight. The second packet is practice questions. This is going to be due on Monday. So tonight, Monday, okay?